Hi students, now I'm going to explain about operation of asynchronous and synchronous counters. We have seen in the earlier lecture, I explained uh, the flip-flops and conversion of flip-flops and shift registers. In this lecture, I'm going to explain about counters. Basically, counter is also a sequential circuit which can count the number of clock pulses which can apply to the circuit. And also there are many benefits about the counters. One of the application of this flip-flop is counter, and then counter which can count the clock pulses, which can measure the frequency divider and frequency measurement, time measurement, pulse width. There are many applications of this counter. So the counter is one of the major application of flip-flops. There are also several types of counter. We can see that the value of the counter represents the number of clock pulses arrived at the clock input. When the clock pulses are counted in an increasing way, it is said to be up counter. Similarly, when the clock pulses are counted in a decreased manner by one of the arrival of each clock pulses, then it is called the down counter. Basically, it is required to count upward and downward direction of a given number. So if counter initially start from 0, then if you want to increase, then we can use the up counter. Initially we store in a number particular outputs in a states of each flip-flops. Then if we wish to decrease the number by 1 each time of the clock, then we can call it as a down counter. An n-bit binary counter, when I am saying binary counter means, so whenever we have taken any number, it is represented with the binary power of 2. That kind of distinct levels existed. So otherwise it is non-binary counter. If you see any n-bit binary counter can count up to n bits. The n-bit count will have n number of flip-flops. And also it has 2 power n distinct output states. Let us see, for example, 2-bit counter has 2 flip-flops. Each bit requires to store each flip-flop, so it requires 2 flip-flops. And also it has 2 power 2, which is equal to 4 distinct states, namely 00, 01, 10, 11. Same way, 3-bit counter will have 3 flip-flops and has 2 power 3, which is equal to 8 distinct states represented by 3 binary numbers or values 0002 111. So these 3 different eight distinct states we can generate with the 3-bit counter. Any binary counter has maximum count limit of 2 power n minus 1 when we start from 0. A 3-bit counter can have maximum of count 2 power 3 minus 1, which is nothing but 7 in binary. It is equivalent to 111. Start from 000. And after reaching the maximum count of a counter, the counter will automatically start for the next clock pulse input and start to count again. Types of counters. Counters are constructed with a series of flip-flops. Based on the input and the clock pulses given to the flip-flops, there are several types of counters. whether we have given the clock pulse synchronously to all flip-flops, or the clock pulse is given to only first flip-flop and the remaining flip-flops are fed with the previous output of the clocks, output of the flip-flop. So based on this, we can categorize of counters: asynchronous counter, synchronous counter, decade counter, ring counter, Johnson counter, like that. So the main difference between asynchronous counter and synchronous counter is that in the asynchronous counter, clock pulse, clock is given for first flip-flop. Whereas in synchronous counter, clock pulse is given to all flip-flops simultaneously. All flip-flops. And decade counter and ring counter, Johnson counter, these counters based on the connections along with this clock pulse, based on the decoding logic, we can call it as ring counter and Johnson counter. You will see at the time when it comes to discussion. It consists of series of flip-flops like a synchronous counter or ripple counter, in which the output of each flip-flop is connected to the clock input of the next higher order flip-flop. The clock pulse is given to the first flip-flop, asynchronous flip-flop. The flip-flops in asynchronous counter are triggered individually. That is, they are not synchronized. So when it comes under like asynchronous counter and the trigger happened individually, then sometimes we can consider that this kind of activity makes this counters get slow. So this type of counters speed is very less compared with the synchronous counters, but it's not all the way, like all the times, but sometimes we can get the asynchronous counters also will get the speed by making different connections. It's also called ripple counter. Asynchronous counters are further classified, we can divide into asynchronous up counter, asynchronous down counter, asynchronous up down counter. We can perform both the up and down counter bidirectional. 2-bit asynchronous up counter. Let us see the operation of the 2-bit asynchronous up counter. For a 2-bit asynchronous counter, it is 2-bit means it requires 2 flip-flops where the counter is increased for each clock pulse. So as the clock pulse changes, every time the count value increases. Once reached to maximum value, again it automatically start from 0. 2-bit counter will have 2 which is equal to 4 distinct states, as I explained earlier, which are called 0, 0, 0, 1, 1, 0, 1, 1. This is the diagram for 2-bit asynchronous up counter. So we can make these counters with the help of JK flip-flop, T flip-flop. Let us see that these asynchronous counters made with the JK flip-flop. So now I'm just explaining the operation of the flip-flop, counters. So how to design, how can we make that counter for a given problem, whether it is up counter, down counter, with a different kind of bit range. That will comes under the design of flip-flops. Now we will see that only operation of the flip-flop. So I can say one thing, that it is a 2-bit asynchronous up counter. It requires 2 flip-flops, JK flip-flop, and I'll also recollect that JK flip-flop, one of the property which we utilized in this case, that to counting the numbers, counting the in the counter. The main property of JK flip-flop is that when we kept J and K with the logic 1, that output will get complement. So when we see that the series of bits, the series of states, which is changes in a binary number. So that kind of logic we can apply by connecting the JK to high state. The main purpose of connecting the two JK flip-flops of JK inputs connected to high means every time we can apply the clock pulse. After application of clock pulse, the state changes. So when the state changes, the output value, where the logic 1 changes to 0, 0 to 1, then automatically we'll get the different state accordingly, like 0, 0 to 0, 1, 0, 1 to 1, 0, 1, 0 to 1, 1. That is what we can see now. So we can have this diagram, take the JK flip-flop, very simple. Take the two JK flip-flops. We know that JK input, Q and Q bar output. And it is a asynchronous counter, so we can apply clock pulse. Main clock is applied to first flip-flop. It is bubbled with the cap arrow, indicates the negative edge clock. So each and every clock with the negative edge clock, it is it is enabled JK flip-flop, and then we will get the output. So, and the first thing is that take the J and K of each flip-flop, both two flip-flops connected to logic 1 or high, so that we can get the change of output by the application of clock provided with directly clock with the first flip-flop, and the indirect clock provided with the output of first flip-flop to the clock pulse of second flip-flop. So first thing is connection of JK connected to logic high. Second thing is apply the clock pulse to the first flip-flop, direct clock, and the output of this Q is connected to input of the clock. And we can measure the states by extending the output QA from the first flip-flop, QB in the second flip-flop. The clock pulse input is given to the first flip-flop only. The output of QA of the first flip-flop is fed as a clock input for the second flip-flop. The higher logic 1 is maintained that JK inputs of both flip-flops. The clock pulse is digitally counted at the output of QA and QB, where QA is LSB and QB is a MSB. Each time of application of clock, we will have the output state changes. We can collect that those state changes can be considered as counting values. At every falling edge of the clock pulse, JK flip-flop 1 will toggle its output state. So initially, for example, we will take the initial value of this one is 0, 0. QA is 0, QB is 0. When QA is 0, QB is 0, it is the initial state. Initially, both are in 0, 0 state. Now, we can apply the clock. When we apply the clock, the output of the first, the first flip-flop gets the toggle output. So what is the first flip-flop? Q output. Q output will get changes because of application of clock, negative edge of the clock. So which is directly connected to the flip-flop 1, JK flip-flop 1. So QA will change state because toggle of output by giving J is equal to K is equal to 1. Next, so it won't connect it directly to the clocks. That's why, because of this, initially we have what we assumed QA is 0. Then 0 means like positive edge 0, we are here 0 to 1, so no changes in the state. So when there is no changes from 1 to 0 in the first this output, so then the QB second flip-flop, second JK flip-flop will remain constant 0 1. Now I am applying second clock. When I am applying second clock, this is first clock, this is second clock. When applying the second clock, toggle of first flip-flop QA, when the toggle of first flip-flop nothing but 1 to 0. What about the second flip-flop? So now we have a 1, logic 1 here in the during the first clock output. So this logic 1 now changes to 1 to 0, means negative edge transition. So changes of this QA from 1 to 0 means negative edge of the change. So the 1 to 0 change in the output of first flip-flop will make to enable the second flip-flop, then it will toggle the output. So that means 1 0. Again it is in 0. So by the application of clock, toggle the first one, and because of this QA is 0, it won't toggle the output logic 1, but the second flip-flop output kept constant, so that we will get the different state. This is 0 0 state, 0 1 statement 1, 1 0 means second state, 1 1 means third state. So after that, both are logic 1 and 1. When both are 1 1, if both are 1 1, what happened? When both outputs are 1 1, now I am applying the clock. I'm applying the clock. After applying the clock, what happened? This is toggled 0. Again the QA is 1, that changes to 1 to 0 means when changes to 1 to 0 in the first output will make the second output enable, so that it will also toggle the output, so that it will go to initial state. In this way, the count start automatically to the initial state. Likewise, we can count the states in a binary counter like ripple counter. When we see that waveforms, this is the clock pulse, the first clock pulse, first negative edge clock, second negative edge clock, third negative edge clock, fourth negative edge clock. Likewise, in the first negative edge clock, initially all outputs are 0, QA and QB are 0 0. When application of the negative edge clock, immediately the first flip-flop go to logic 1, and because of this QA is 0, 0 to 1 change, no change in the second flip-flop, so we can keep constant 0. That state is called 0 1 nothing but 0 1 nothing but first 0 state, first state. Then in the second negative edge of the clock, this is toggled automatically. The first flip-flop toggled, just go to 0. Whenever first flip-flop output goes to 1 to 0, which will make them the second flip-flop gets toggled. So that's why just go to 0 to 1. 0 1 means from MSB to LSB 1 0, we can call it as state 2. And then again apply the third clock, will make the toggle 0 to 1, and again 0 to 1 change won't make any change in the flip-flop in the second output, so it will be kept constant. Then after that, again apply the clock pulse, then it will change to 0. This 1 to 0 make the second flip-flop changes, so that it will also change to 0. Again it will go to reset. So in this way, we can see that the ripple counter, the similar operation for up down counter also, but only changes with the connection. 3-bit asynchronous up counter, only the thing is that it requires 3 flip-flops. We use either a JK flip-flop or T flip-flop, which will count the 8 count states 0 0 0 to 1 1 1. The counter counts the incoming pulses start from 0 to 7. So as I said, it requires 3 flip-flop. Whether you can use the JK or T flip-flop, because when we use T, just we can join together. So JK, when we join together and given one input, is nothing but indirectly T flip-flop. So take the T flip-flop, 3 T flip-flops, connect J and K terms, like K inputs. Both J and K inputs are connected to common high input, and the clock pulse is applied to the first flip-flop, and output of the positive, positive output is given feed to, next second flip-flop input, clock input, and then second clock input output is connected to third clock input. And here one interesting thing is that basically the simple logic for connecting for up and down counters. So for example, we have a two triggerings, negative trigger and positive trigger. If the trigger is clock trigger, if the trigger is negative in the asynchronous counter, and then the output of first flip-flop is a positive output, like Q output. If it is Q output connected to the input of second next following flip-flop, we can make those connection for up counter. Same thing, if you use the positive edge trigger and Q bar is connected to Q bar of the previous flip-flop is connected to the next flip-flop clock pulse, then also we can utilize it for up counter. Suppose trigger is negative, Q bar is connected to the next flip-flop, then we can have a down counter. Positive trigger, Q value is connected to the next flip-flop input, then we can also down counter. Simply we can remember for up counter, we suppose if you feel it as a plus, Q means Q plus, Q bar means Q minus. So minus negative trigger with a positive Q, positive trigger with a negative like Q bar is made with which makes utilize for up counter. In order to design the down counter for negative, negative, positive, negative trigger for Q bar input, Q bar output of one flip-flop to connected to the clock input for the next flip-flop, then it is for down counter. So both signs, negative trigger, Q bar, positive trigger, the Q is connected as a flip-flop counter. The Q is connected as a clock input. We can also design the down counter. So based on that logic, I found here. So first flip-flop directly connected, it is a negative edge. So negative. When clock is negative edge clock, the output of the first flip-flop is the output of Q is connected to the clock input of the second flip-flop. Then this connection is for negative plus positive. So up counter. It is a up counter. Three-bit up counter. We can get the three states. The clock pulse count is noted at the output of each flip-flop QC, QB, QA, where QA is the LSB, QC is the MSB. Each and every falling edge of the clock pulse, the output of first flip-flop toggles. After that, each logic high QA is equal to 1 of JK flip-flop 1 at its falling edge JK flip-flop 2 will toggle the output. So every time the preceding flip-flops changes from 1 to 0, that will make the toggle of next flip-flop output. In this way we can get the states. So this is the waveform for the 3-bit counter. Then we can see the down counter. Down counter will count the clock pulses from maximum value to 0. In other words, for each clock pulse, the count value is decremented. The clock pulse input is given only to the first flip-flop, as I said earlier. The clock input of remaining flip-flops is triggered by the Q output of the previous flip-flop. And also, if it is down counter, indirectly, if it is negative trigger, the Q bar is connected to the clock pulse. And if it is positive trigger, Q output is connected to the next flip-flop. This is the diagram. If you see here, if it is negative edge clock and JK is connected to common high, and if it is a negative and we can connect the Q is connected to the clock, so negative and Q bar, it is a negative edge clock, we can connect to Q, then we will get this down counter. This is the waveform for down counter. This is the each and every negative edge clock. The QA is toggled. When the QA is toggled 0 to 1, QB is initially 0, so kept 0. So QC 0, kept 0. So, sorry, it is all ones. So we can take the output here. There are two ways. We can collect the output in a complement form. So we can have all ones. So once the negative edge clock, that will change to 1 0, 0 1 1, which is represented as 6, and then 5, and then 4, 3 2 1 0. Up down counter, asynchronous up down counter, are also called bidirectional counter. In this counter, it is the counter made with some combinational logic along with the flip-flops. So if it is 3-bit counter, up down counter, it requires 3 JK flip-flop, like T flip-flops, connected T flip-flops, and then clock pulse is connected to input. The remaining, like first flip-flop output, connected through some logic, combinational circuit. So here it is control and up down counter, input, control input. When the control input is 1, this one is connected to AND gate 1 and AND gate 3. So AND gate 1 and AND gate 3 are enabled. That means in the previous lecture, as I mentioned, whenever any enable control input is high at a particular AND gate is connected, that AND gate will act as a path. Okay, this is the path. This path is connected to OR gate, that will make the next output will make the other flip-flop enabled. So whenever it is on, logic gate 1 and gate 3, and gate 1 and gate 3 enabled, and gate 2 and gate 4 automatically disabled. When automatically disabled means 0. When one input is 0 of the OR gate and one input of the 0 OR gate, it only passing of logic from first AND gate, 1 and 3 AND gates only. So what does it mean? Whenever clock pulse is negative edge clock pulse, first flip-flop is triggered, toggled. The toggle output, if it is 0 to 1, no changes in the second flip-flop. If it is 1 to 0, that 1 to 0 will make this negative edge triggering to the second flip-flop, so that output of JK flip-flop 2 is changes. So in this way, the path is created through AND gate 1 and gate 3 for control signal is 1. That means the control signal is 1 means it is a up counter. If it is that value is 0, it is a down counter. So in this way we can design the up down counter. Synchronous counter. Next, the synchronous counter is also an application of flip-flop. If each flip-flop in counter is triggered at the same time through the clock pulse input, it is said to be synchronous counter. To design synchronous counter, the toggle flip-flop or T flip-flop is used. The clock pulse is given to all flip-flop in the counter. Asynchronous counters are further synchronous counters are further classified. Synchronous up counter, synchronous down counter, up down counter. 3-bit synchronous up counter. If you see this, there are two important things need to be observed. One thing is clock is connected to all flip-flops, and then the TA input of the first T flip-flop is always maintained at a logic high. The output of T flip-flop 1 is fed as an input to the input for T flip-flop 2. The QA and QB output of flip-flop 1, flip-flop 2 are ANDed together, and its output is given to the flip-flop 3. The output states of the counter can be observed. QC, QB and QA as shown in the figure. So we can have this synchronous counter connecting the clock to all flip-flops simultaneously with a bubbled cap, negative edge clock. First T flip-flop connected to high, so that each and every clock it will get toggled. The second flip-flop input is connected with the output of first flip-flop. The output of first flip-flop directly connected to the input of second flip-flop. But what about the third flip-flop input? The first flip-flop output and the second flip-flop output are ANDed together, and output of that one is connected to the input of third flip-flop. This kind of logic, and along with the clock simultaneously, we will achieve the synchronous up counter. The waveform for synchronous up counter. So if you apply this negative clock like this one, and then when clock negative edge clock, initially all are 0 zeros. QA, QB, QC are zeros. When negative edge of the clock, what happened in the first flip-flop toggle? We will get 0 to 1 change. When this 0 to 1 change, so the output of first flip-flop connected to input of second flip-flop. So 0 to 1 change in the T flip-flop, no change at all in the second flip-flop. So it kept constant. What happened in the third one? Third one is ANDed of QA, QB. What is QA, QB now? 1 and 0. 1 and 0 in the AND gate will make 0 input in the TC. And at the same time clock pulse, when 0 is given to TC, no change in the state, unchanged. When T is equal to 1 only, it will change the state in the T flip-flop, as we know that. Next clock. In the second clock, toggle the first flip-flop. This output is given to second one. So this 1 to 0 changes, logic 1, and then it will toggle, you will get the 0. This 0, then at the same time, already we have a 1 in the synchronous clock of 2, that will toggle the output so that we can get the QB1, and we have already QB is equal to 0 in the during the second clock changes. So this 0 won't change the third one. In the third clock, what happened? For example, third clock, toggle the first one, like this 0 toggle, will get 1. So we have a QA is equal to 0 at the time of changes in the negative edge clock. So this 0 won't change, it will keep the second flip-flop output. To get the third flip-flop output, the AND gate of QA, QB. What is AND gate of QA, QB are the just before, just immediate of this clock, 0 and 1. 0 and 1 AND gate will get 0. So 0 of T input won't change of any output, so 0. So likewise, you will get the states 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Likewise, we will get 7. Let us see 7. 1, 1, 1. So all QA, QB, QC outputs are 1. Now, when applying the clock, when a negative edge of the clock, the first flip-flop changes its toggle of output. We'll get 1 to 0. So this one is available just before the it is a every time you can remember that the application of clock simultaneously at the same time you can feel it. When a negative edge clock, the first flip-flop toggle at the same time, the input of input of TB nothing but output of Q1 1 QA 1. So that will make the changes. So it will also changes. And what about third one? AND gate of both Q and QB. This one and this one. AND gate of 1 and 1 only. So whenever 1 is available at TC at the same time of the 8th clock, you will get the toggle. So 0. So you'll get the reset mode, initial state. Then it will start again. The states from 0, 1, 2, 3, 4 like this. This is a synchronous clock counter operation. 4-bit synchronous up counter. Similarly, we can use 4 flip-flops. And first flip-flop input is T input is high. Second one is output of first flip-flop directly given to second one. Third one is AND gate of previous 2 outputs. Fourth one is AND gate of 3 previous outputs connected with AND gate, and we can give it as an input of the T flip-flop. In this way we can design the up counter, 4-bit up counter. Operation is same, waveform is same. So it will count start from 0, 0 to 4 ones means 15. Again once reached to the 15, it will get back to its reset mode. So in this way we can count. Similarly, up down counter, bidirectional counter. In the bidirectional counter, same way we can use this high input at the first. The second and third one will provide with the counter, counter control input. That control input will directly connected with the logic, decoding logic. When control is 1, up down counter, control signal is 1, odd number of gates are allowed, enabled, and control up down counter value is 0. That means down counting through second gate and OR gate and connected to TB, fourth gate and OR gate and TC. This is the path so that we can count the down. So we can achieve up and down counters this way. I will take one case to explain that one. Let us take internal input is 1. When it is 1, logic like an AND gate 1, AND gate 3 are enabled. When they are enabled, that means this is 1, which allows whatever the logic and the second input that will pass through the OR gate. What does it mean? Second and fourth gates are 0 means 0 inputs are available at a OR gate 1, other OR gate. So whenever it is 0, fixed for 0 every time. So whatever the logic of up counter, for example, first clock, negative edge of the clock, initially all are 0 zeros. So this, because of this I is connected to the T flip-flop, toggle of output. So we'll get 1. When you will get 1, that 1 is available in the AND gate 1. 1 and 1 is available at OR gate 1. So it is a synchronous clock. So at the same time, what is the output of QA? 0. Same time, we will get this TA. So this one 0 is given to 0 is applied TB. So we will get constant 0. And similarly, we will get a constant 0 because no change in the third. What happened in the second? In the second clock, so we have a toggle in the output of first. But what about this? Previously we have a QA is 1. That will 1 into 1 of AND gate will get the 1 in 1 logic 1 input to the OR gate. That will give the 1 to the TB. That will change the toggle of QB. So you will get the toggle in the QB. What about TC? This is connected to logic 1 connected to 3. And also QB output, what is the previous QB output is 0, 0 into 1, this 0, this is 1, 0 into 1, 0, two inputs are 0 in the OR gate, that the 0 is available at TC at the third clock, second clock. So this 0 makes keep constant of the same previous state in the third flip-flop, so 0 only. That's why we can get this 0 0 0 0 1 0 1 0, in binary, in a decimal form, 0 1 2 3 4 5 6 7. After again it will reset to 0. In this way we can count the up counter. If you give the control up down counter input is 0, the same the second and 4 AND gates are allowing, which enables the TB flip-flop, TC T flip-flop 2, T flip-flop 3, which will be utilized as a down counter. This is the diagram, same diagram, but we can control signal is 0. That is the only difference. We will get the down, 7 7 to 0. Again we will get 7. Likewise we can count the counter. This is about counters. So these are the simple operations of synchronous and asynchronous counters, mainly binary counters like ripple counters, up counter, down counter, with any number of range, like any n-bit counters. Let us see asynchronous counters like ripple counters and Johnson counters. We'll see in the next lectures. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.